Okay, we've seen that the sphere of radius 1 centered at the origin in the first octant can be described by three inequalities: x going from 0 to 1, y going from 0 to the square root of 1 minus x squared, and then z going from 0 to the square root of 1 minus x squared minus y squared. In general, we saw earlier that a volume integral for a simple surface, which the sphere is, above the xy region, because of the way this is partitioned, our z runs from 0 to z of xy. Z of xy in this case is 1 square root of 1 minus x squared minus y squared. From 0 to y of x being this function in the xy plane, and that's going to be from 0 to the square root of 1 minus x squared, and x going from 0 to a, whatever this interval is. In the case of the present integral, this will be from 0 to 1. So we should be able to write down our integral. The volume would just be the integral with respect to z from 0 to the square root of 1 minus x squared minus y squared. I'm going to regret using this fat tip marker and putting my integral signs that close together. Okay, anyhow, y goes from 0 to the square root of 1 minus x squared, and I'm going to abandon that fat tip and see if I can work that in. It's not pretty, but I think it can be read. And x going from, okay, so that's with respect to y. Let's go back to the fat tip. And then from 0 to 1 with respect to x. The integral is easily enough evaluated using standard integration techniques, and we'll save that for the next clip. If we had a density function, so we have a density delta of x, y, z, then the mass is going to be the same triple integral, or the triple integral over the same region. If you can read all that, of the density function. Because of the way density is related to volume at the level of the smallest increment, it turns out that we just insert the density here before our volume increment, so that our integral would be this definite integral. I haven't specified a density function. But the result is going to look like this. Whatever the density function is, we just plop it in right there. We could integrate any function. Integrate any quantity f of x, y, z over our three-dimensional region, and the integral from 0 to the square root of 1 minus x squared minus y squared with respect to z, 0 to the square root of 1 minus x squared with respect to y, 0 to 1 with respect to x, whatever f of x, y, z is. If we can integrate this function with respect to z, then when we plug in 0 and square root of 1 minus x squared minus y squared for z, etc., we get a function of just x and y, which hopefully we can integrate with respect to y. Plug in the limits 0 square root of 1 minus x squared, giving us a function of x, which hopefully then we can integrate with respect to x. The interpretation simply depends on the meaning of whatever f of x, y, z represents, multiplied by delta z, delta y, delta x. That is our volume increment.